All right, ladies and gentlemen, good morning to you guys. It's kind of odd. Good morning to you guys. I hope you guys are doing well. Give me a like if you can hear me, and hopefully you guys can hear me. At least on my end, it says you can as I scroll through everything we're working on. Just looking at some things that we were working on. Okay, the likes are coming on in. Thank you guys so much. All right, let's go over to the browser. We'll check our internet speed, see how we're doing this morning with that. Let's. All right, looks like we're at 39.2 megabits per second. And ladies and gentlemen, so set YouTube to 1080p to maximize your experience. And we're going to look over some administrative chores here. So I sent you guys a few things that over the holiday that I said I would. And what I have here is the proof for the fundamental theorem of calculus. So I did send that to you guys this weekend. But I also did another thing. And I think there's an issue with this one. It's not even there anymore. So I'd have to double check and get that one. I think I know what happened. So I'll resurrect this for you guys. I did a couple of examples of numerical approximation to area under a curve, where you can actually see us using the TI doing it. So I wanted to show you guys another example of using the TI, since you guys may have these kind of calculators as opposed to Microsoft Excel or something. So I did that, and I'll get that back up and running for you guys hopefully today. I do have a meeting today at 12:15, a very important meeting, so I won't have my office hours after around 12:15. They'll be cut short, today, because this is somewhat of an important meeting. And anyway, so that's what's going on, and we're gonna go to worksheets and videos, and I'm gonna go back down here for us. And I believe we were working on this worksheet. No, we weren't. Anyway, we weren't working on this one here, but okay, we will start today to work on some of these integration problems. I think we're working at this definite integral. Yeah, we're working on this worksheet for you guys, the other day, but we're going to kind of regroup and summarize these things. And, anyway, I guess we had that. So we're working with some of these. Interesting. So I'll put them both there. Go back. Indefinite integrals. All right. So put down some properties here for you guys today and start working with some more integrals so we could get good to go on this. Yeah, some of these properties. So here's kind of the things we want to work on today here. Yeah, all right. So, okay, so let's go back here. Let's go to the iPad. We're just going to title this integrals. How's that? Get a new one. There we go. All right. And we have these indefinite integral properties. You have the integral. C is a constant. That'll be cx plus some big C. And I think I did write down some of these properties for you guys already. Constant times a function. Pull out the constant, and you can integrate the function. Okay. 3. Integral of a sum or difference. That'll be sum or difference of integrals. Power rule. X to the n plus 1, n plus 1 plus c. So I started to write down some of these indefinite integral properties for us. This is what's general form. Now we're going to write down properties in terms of our trig integrals. So these are antiderivatives there. The antiderivative of sine is going to be minus cosine. And the antiderivative of cosine is sine here, ladies and gentlemen. So these are some properties. Remember, secant squared. This will be tangent here. Cosecant squared minus cotangent. Secant tangent. This would be secant. Cosecant, cotangent will be minus cosecant here. So we're going to have these, what we call these indefinite integral properties, okay? And I started to talk about these already, some of these here. And these are what we're going to use. And then we have the fundamental theorem of calculus. Fundamental theorem of calculus essentially states that if we integrate, if we now have limits, notice the top properties have no limits. If we have limits here, we have the antiderivative notation here. This is x is a, x is b, but if we have to have f be continuous. Over the interval ab. And we were looking at this idea, you know, before the break. So we want to kind of, you know, look at some of these examples and some of these properties here of how to use things here. We're going to go over a bunch of them. And we have to be masters of integration. So, you know, they can give you something like this, x plus the square root of x minus 1 dx here. Now I'm going to give you this general form here without limits. So I want you guys to know we don't have any limits. This is without limits, and that's fine. You know, we're going to give the general form here of these integrals, and, you know, we're just going to have to find antiderivatives here. So to remind people, you don't have a property here called the product rule. Okay, there is no product rule property. So I want you guys to know something important. You can always tell somebody who hasn't done their homework. They think there's a product rule, and there isn't. So there is no product rule for this kind of question. And so what you'll end up doing really is doing a little bit of algebra. So yes, this is x squared of x minus x, just doing some algebra here. And ladies and gentlemen, we still have more algebra to do. This is x times, x to the 1/2. So if you want, you can do your algebra here in purple. And this is really going to be x to the 3/2 minus x. So this is what we're going to integrate. Now, again, there's no limits, and I'm going to show you how you handle that when there's no limits. Okay, limit of a difference is difference of limit. So you're going to do these properties now. Okay. So what you now see, there is this property, difference of limits is limit of a difference, or an integral of a difference is difference of integrals. I apologize for that, and that's right in here. Okay, this is why we put plus or minus. This is property number 3. So we're going to use these integration properties. You don't have to. You could just find antiderivatives. But then now you say, what property should I use here if you want to go with properties? Well, that's the power rule again for the first one. The second one is also power rule. And you might say, do I put plus c and then plus c here? And I can say, well, you have two integrals. You could put c1 and c2. So it'll be x to the 5/2 over 5/2. You say plus c1 minus x squared over 2 plus c2 here, ladies and gentlemen. Okay, because you have two integrals. And that'll give you 2/5 x to the 5/2 minus, you can say 1/2 x squared plus c1 plus c2. Now, people can get bogged down in this constant stuff. And I'll just say at the very end, just put a constant c, because c1 plus c2, those are just saying we're adding constants there. And so that'll be just a c. So notice by these properties of integration, we did this difference rule, and we also did the power rule here for number 4. So we did this rule as well, 3 and 4 here. So what you now end up with, ladies and gentlemen, is an answer here. And you might say in back of the book, you might see something that looks like this. You see 2/5, and then you say, well, why do they have x squared square root of x minus 1/2 x squared plus that constant? Well, they have that because, ladies and gentlemen, what they're doing now is they're simplifying this rational. Because 5/2 is 2.5. Right, remember, this is as a mixed number, that's 2.5. So this is where this came from. So, you're looking at an antiderivative. If you wanted to do it that way or using properties, either way is fine. But the idea is for you to start to get used to this notation and properties. And they didn't give you any limits, which is why you're giving the general version here. There's no limits here to evaluate. So this is what we call the general family of solutions. This is the general version because you have that constant c, where c1 plus c2 is just your c. Excuse me. So ladies and gentlemen, this is kind of what we're looking at with all these properties. And they're going to give you a lot of different kind of examples here, of how to approach this. They can say, this is x minus 3 over the square root of x now, as an example. No limits. Okay, so there's no limits. We're going to look at the general version. And to remind people, there's no quotient rule. So don't look at it this way. I'm going to ask you guys to do a little bit of algebra. Give you a few minutes to try some algebra right in here. What algebra would you use here? See what you guys get. All right, let's see. Do some algebra. This is x over the square root of x minus 3 square root of x. That's under the that's under the integrand, I should say. So yeah, x to the 1 minus 1/2 minus 3x to the minus 1/2. Let's double check here. Yeah. X to the 1/2 minus 3x to the minus 1/2. So we're integrating here another difference. We do have a property for the difference. Right? So this would be using properties. X to the 1/2 dx minus 3 x to the minus 1/2. This is integral of a difference. Difference of integrals. Now I want you guys to also notice you got a constant. So we can pull out that constant now. Okay. Go back to the property list. Here we go. Pull it out. Pull out your constant. There it is. So, power rule now. X to the 1/2 plus 1. 1/2 plus 1 plus a C1 minus 3. Here's every detail. Negative 1/2 plus 1 over a negative 1/2 plus 1 plus another constant, because you have two integrals. Okay. X to the 3/2 over 3/2. Do your arithmetic. Minus 3. X to the 1/2 over 1/2 plus a constant. So 2/3 x to the 3/2 plus C1 minus 3 2x to the 1/2 plus C2. So we can do some more algebra. We can distribute. That's 6x. You can say, is that minus 3C2? It is, but let me kind of remark about these constants here, okay? What you can simply say at the end of the day, that's just going to be a constant. Even if you have C1 minus 3C2, just put your answer here plus a C. There's a constant. You don't have to do really the algebra with constants, because it's just like saying there's a number. Remember, this is a general form here. These are called indefinite integrals. Indefinite integrals have no limits. Okay? And note, definite integrals have as a number. Definite integrals essentially have limits. Answers are numbers. These are indefinite. They're general. So you just have that constant. All you really have to worry about is, this portion here. So you may look in back of the book and you might say, they gave me an answer, 2/3 x square root of x minus 6 square root of x plus a constant c. This is what they're looking for. This is a family of solutions. This is general. This is indefinite integrals, because there are no limits here. And they did simplify writing x to the 3/2 as, remember, this is 1 and 1/2. So they simplified that exponent and wrote this as x square root of x there. So this is kind of, again, this is another great example, but this is showing people that, you know what? You don't have a quotient rule. You don't have a product rule. You only have a sum and difference rule, and you can pull out constants. So you're very limited. So these are the properties that you're going to be using here for these, ladies and gentlemen, and it's an important kind of thing to know. These are very important. Anyway, good questions there. Okay, give you some more examples here. They could give you an example of something like maybe x squared plus 4 here, dx. Using properties again. Now, these are indefinite because there's no limits. We do have the integral of a sum is sum of integrals. So they do have a sum property. So, okay, there's a sum there. And then, again, notice you have here a constant. So I can use properties and I pull out the constant 4, and I have that dx. So here's my constant now. Okay, now I'm going to go back to the comment I made about my constants, because you can put constants all over the place. You don't have to do algebra with constants. So here's what I'm going to say. This is what I think it's important to do. We have now two integrals. Here and here. Now, I've been used to doing this as a highlighter. Okay. The first integral, by power rule, one-third x cubed plus 4x. The integral of dx, this integral, is x. Now you can put this plus c at the end of the day there. You don't have to put your c1s and c2s. And so this is how you get your answer here. And I think maybe if you wanted, should we put that as a property? Maybe put that as a property number 11 here. We'll put that as a property because you're going to see that over and over again. So maybe I'll just call that property 11 right in here, right? If you ever integrate dx, the answer is really x plus c. Okay, now I'm going to express why that is. So I'm going to give you guys a proof. You might say, well, why is that? Let's put this way here. Because this is like the integral of 1 dx. That's your function. Think of it as x to the 0 then. And so by the power rule, you get 0 plus 1 plus that c. X to the 1 over 1 plus that c. Which is really just x plus c here, ladies and gentlemen. So when you see this one here, just integrating dx, think of that as just x, and they can add your constant, and then this is why we ended up with that final answer here. So we're using all these nice integral properties, and they come from that antiderivative environment there. So I'm giving you guys a lot of properties here. Okay. All right. Now, another example here. Onward and upward, these nice integrals. Pi Sine X Dx. Okay, just using all the properties that we started the day with. What you want to notice is you do have a property that pulls out a constant. Pi is a constant, it's not a variable. So now we just have to integrate this sine. We have to know what the integral of sine is. Now, we wrote that property down, integral of sine here. So let's go back to the integral of sine. Oh, that's minus cosine. You could use antiderivative, as well, like we've been doing last week. But let's show you all the little gory details, because the devil's in the details. It's not that bad. It's doable. You can say, is this minus cosine plus c for this particular integral? It is. You'll distribute, which means you get minus pi cosine plus c pi. And you go, well, is that c1? C1, but again, you're in that mode that this is just a constant. So this is minus pi cosine plus just that constant c. You don't have to do algebra with constants, and just leave that as a c. Again, there's no limits, so we don't have to evaluate it. And that's kind of what is happening with us now here for this question here. So ladies and gentlemen, these are some very, very good questions here to go about, and we do have these kind of examples. All right. Similar to the following. They said, what is 2 cosine? Very similar. Pull out the constant. 2 integral cosine. And if we know that integral, and we do, right? These are antiderivatives. Derivative of sine is cosine, so that's going to be sine x plus c. Now, remember, ladies and gentlemen, I would say to you, if you know this integral, you don't have to do the algebra again with, you can say, is that 2c? Okay, then change that to c1. Call this constant. Just call it c, but you could just simply have said, I'm going to just say 2 sine x plus that c constant at the end, and I'm done. I could just not pay attention to the algebra of constants and get stuck with that algebra. But, you know, some people do. I used to be a student that did that. I used to put C1 and C2 just like I have here with you guys. I used to do that stuff because I wanted to know every detail, ladies and gentlemen. I wanted to understand things, and that's how that works. So I'm just going to let you guys know that's how you can try that one out as well. You know. But you will eventually just put C at the very end because you get started doing the algebra of constants and you don't have to. You know, and then you can have 3x squared minus 5x plus 2. You know, this is, again, there's no limit, so this is an indefinite integral. You know, they're trying to use this to get properties here, get you guys used to properties. Okay? So let's use our properties. Integral of a sum and difference, we do have those. 3x dx minus integral of 5x dx plus 2 dx. Pull out your constants. 3 x squared dx minus 5 x dx plus 2 integral dx. Okay. 1, 2, 3. So we have 3 integrals now. 3 times 1/3 x cubed. That's the first one. You don't have to put your constant. You don't have to be stuck with the algebra of constants. So you get 1/2 x squared now. Plus 2. This will be the x. Just put the constant at the very end here, ladies and gentlemen. So let's put that in red, or at least highlight that in red, so that you don't have to get stuck with the algebra of constants. Just put a plus c at the very end. And what you have found here is the antiderivatives. You've used the power rule essentially for these. And there you go. So, ladies and gentlemen, we are practically done now. This is going to be final answer. 3 times 1/3 x to the third minus 5/2 x squared plus 2x plus the constant c. And you're done. There we go. And there you go, ladies and gentlemen. This is, you know, doing some integration. We're doing some nice integration here. Give you some, lot of examples here. Square root 25 x cubed. Oh, we'll just put an x. dx. Okay. Now, you're going to have some algebra here. So the quotient rule for radicals is what you're looking at. And this is just going to be 5 square root of x, which gives you 5x to the minus 1/2. So we're going to integrate 5x to the minus 1/2 dx. We get to use our properties. We get to pull out our constant. So this will be 5 integral x to the minus 1/2 dx. You pulled out the constant. So add 1 And then just put your plus c at the very end, so you don't have to worry about the algebra of constants. You just worry about your arithmetic. So this could be 5 x to the 1/2 over 1/2 plus a constant, or simply 5 times 2 square root of x plus a constant. The answer is 10 square root of x plus c. And ladies and gentlemen, here you go. You're done. And, this is how we actually integrate here. Okay, so there's kind of a lot of different kind of looks you guys can see with these kind of questions. They can even give you, for example, cube root of 8x squared. Algebra. Properties. Cube root of a product. Product of cube roots. This would be x to the 2/3 power now. 2x 2/3 dx. Pull out a constant. So we pulled out the constant. Now integrate. 2 2/3 plus 1 plus that constant. 2. This is now going to be, remember 1 is going to be 3/3. So 5/3. 5/3 plus c. And we're going to end up with 2 times 3/5 x to the 5/3 plus c, which is going to be finally 6/5. Now remember what 5/3 is. 1 and 2/3. X to the 2/3 plus c. 6/5 x. Cube root of x squared plus c. We have rationalized that, or we're using our properties of exponents, writing the rational exponent as a radical. And there you go, ladies and gentlemen. This is another good example of what they expect and how to integrate. All right. Now remember, there is no product rule. So you don't have a product rule. So you might say, well, if there's no product rule, then what am I supposed to do? Algebra. By the algebra, FOIL. X squared would be minus 4x minus 5. So now use these properties here. Make sure you did your FOIL correctly. Right? Okay. So by properties now, there is an integral of a sum, integral of a difference property. Pull out the constant here. Constant. Okay. So, first integral. 1/3 x cubed minus 4 times 1/2 x squared minus 5x plus c. So we found every one of these integrals here. This one, and then you add that constant at the end. Okay, let's simplify. 1/2 x squared minus 5x plus c. And there you go. So just looking at the algebra here for some of these here. Okay. Here we go. 1 minus 3 secant squared. I apologize. Thank you, Renee. You are correct. Yes, it would be 2. I'm listening to some sport news, and it looks like Max Scherzer is signing with the Mets, which is breaking my heart at the very moment, so I apologize. Yeah, I did. Thank you. Thank you, Daniel. Those who care, Max Scherzer looks like he's signing with the Mets. I'm multitasking, so you're correct. And we can put this as a plus. Okay, properties. Remember, our focus is on using these properties here. Dx plus the integral. There is an integral of a sum property. And we get to pull out the constant. Okay. This is x. Antiderivative of secant squared. That's tangent. And then to add your constant at the very end. So x 3 tangent plus c. And there you go. Okay, 1 plus x squared, or yeah, let's look at some of these here again. We're going to have some algebra here. Two minus x squared, 2 minus x squared, 2 minus x squared. That's the third power. So you're going to have to multiply here. You know, do a whole bunch of multiplication here on this. All right. Multiply the first two first. 4 minus 4x squared plus x to the fourth, 2 minus x squared. Then multiply again now. So multiply the 2 with everything, so you get 8 minus 8x squared plus 2x to the fourth, and then minus x squared, that's minus 4x squared. Plus 4x to the fourth. Looks like that's minus x to the sixth. Double check, ladies and gentlemen. 8 minus 12x squared. 6x to the fourth minus x to the sixth. So, integrate. Double check, ladies and gentlemen. properties. Pull out the constant. Okay. 8x, 12 times 1/3 x cubed, 6 x to the 5th over 5. And you could do it this way. I apologize. Here we go. 8x minus 4x cubed, 6/5 x to the 5th, 1/7 x to the 7th plus that c. And there you go. So this one did have some algebra. You had to cube everything. And there you go. All right, let's use our properties here. Okay, now remember, this is going to be, we're not going to integrate yet. Pull out the constant. Okay, integrate. X to the 7th over 7 plus 3x minus x to the minus 5 over minus 5, because negative 6 plus 1 is negative 5 plus the constant. So we get 1/7 x to the 7th plus 3x plus 1/5, and that's going to be in the denominator now. There you go. There it is. Six cosine plus 2 sine. And they might put that in a bracket. It's the same as a parentheses. 6 cosine dx. Oops. Let me give you every property, ladies and gentlemen. Integral of a sum is sum of integrals. Pull out your constants. Now I need integrals for cosine. See, the derivative of sine is cosine. So this one is going to be sine. The derivative of cosine is minus sine. So this would be minus cosine. So you get 6 sine. And this is going to be 2. It's going to become negative because you have a positive times a negative. And don't forget to add your constant at the very end, ladies and gentlemen. And there you go. This is how we, find some of these values here. And so now we can get some other interesting kind of questions here. All right. Cosine squared. And this is kind of another area where I would say to people, you know, like you talk to trig students, and there's a reason why you spend all the time that you do, you know, you working with trig identities, to proving trig identities. But you can't use one here, you know, because this is not a difference. This is a sum here. So you might say, well, I spent a lot of time using trig identities. I want to put that as a use Pythagorean. It's a Pythagorean identity. It's not a Pythagorean identity. So you go, okay, then what is this? Well, you know, we're going to use some algebra. And the algebra now, we're going to divide both of these here by divide the sum here. So it was actually easier if we just use a little bit of that algebra. Now this is where the identity comes in, that's secant squared. And this is anything divided by itself is 1. So we did use an identity, but it's one of the simplest identities. It's a reciprocal identity. So we now have a nice secant squared plus 1. Now that should be ring a bell. And you go, well, first of all, integral of a sum is sum of integrals. But what I mean by ring a bell, this integral is tangent, because the derivative of tangent is secant squared. And this will just be the x plus c now. So that's what I mean by ringing a bell. So some of these use of identities with trig functions will come into play here for us. So we went through some examples there. You know, but not always, at least in the beginning. They want to know if you can actually identify these antiderivatives, you know, and using some properties in the beginning, and they'll throw in some algebra. So, you know, factor out that constant, and then here you got the integral of secant tangent. So they want you to know, oh, we know the derivative of secant is secant tangent. So this is just secant. Okay. So you got the constant outside here, and that's what they wanted you to recognize. So that's part of this, is recognizing some of these integrals and working with some of these identities here. So we'll give you guys another example here. Or this is a trig integral. Sine plus sine tangent squared secant squared. Okay, so we kind of look at this one here, and you may notice that, oops, algebra. So it looks like for the algebra, I can factor out a sine. I get 1 plus tangent squared. Over secant squared. So at this point, ladies and gentlemen, you may recognize by using identities after you factor this out that this portion here, there is a Pythagorean identity. That's secant squared, Pythagorean identity. So to let you guys know, in my trig class, I think even in this class, Here's a trig cheat sheet. We'll give you guys that cheat sheet if you want to review some of your identities here. It might be a good idea. All right, so here's some of that cheat sheet here. Get rid of that secant squared. So this is just the integral of sine here. You know. And to integrate sine, you might say, what's that integral? It's minus cosine plus c. You know, and then just to say, by the way, I'll give you a by the way here. I'm going to ask you if this makes sense. This integral makes sense. I'm going to copy here this for you guys. Does this make sense? Let me copy this here. Okay. So Oscar is saying something here. He's saying, does this go, wouldn't it turn into 1? And actually, Oscar, yeah, it does turn into 1. This is why I canceled here. This is secant squared here over secant squared. That's canceled. But you're just left with the sine function now. And that's why sine is right here. So that did turn into 1. We did do that. But you do have that factor of sine, because remember, you factored out the sine originally here. We factored out this sine here because it was common. That's why it's out here. And yeah, the secant squared over secant squared x is canceled, but you do have that factor of sine, so you integrate the sine, and that's minus cosine. But here's my question. Does this make sense to you guys? I added limits, so this is now, I want you guys to note. This is a definite integral. Does this make sense? And we're really asking is, can I apply the fundamental theorem of calculus for this question here? Because now you got these limits. So I'm going to ask you guys to think about this. I'm going to put some homework for you guys in your textbook. And we're out of time, and we'll talk a little bit more about this tomorrow, but enter your name in the comment section for attendance purposes and get started on your integrals as soon as possible, ladies and gentlemen. All right. Take care. Have a great day and stay safe. We'll see you guys later.